Good morning, all. Welcome to the next class of data structures. Last time we have discussed merge sort, and I'm sure most of you have been able to implement the same. For those who could not implement, I'm just sharing you some partial code first of all. Those who could not make at all, for them, this is the way we should have started. I should have made a merge sort function, which will be recursively called based on some criteria, stopping criteria. If not met, we will be doing the recursive call. So condition you should be able to identify, calculate mid, call the recursively merge sort for the first sublist, left sublist, call the second sublist from mid plus 1 to end. So start and end are the starting and ending indexes for the list being sorted. And once two individual lists are sorted, merge sort, then they will be merged together using a merge function. So merge function will require start, mid, and end being passed, where automatically means first list is a start to mid and second list is mid plus 1 to end. I've taken a temporary array. So my I equal to start, second list starts with j, mid plus 1, and k being used for storing into temp. K need not be start or end. K can be always with 0 because the temp can be used from 0 onwards. Loop here, obviously a kind of a while loop because we don't know how many times we will iterate. And if my left sublist element or first sublist element is smaller or equal to the second sublist element, then I will copy that into my temp array and accordingly I or k will be incremented. Else you should be able to think similarly. Once you come out of the loop, all elements have been there, and then you should be able to copy remaining element based on I into the temporary array. Copy the remaining element based on j. So one of the list will be empty, other list needs to be copied. Once you have done this, then you have to copy back the temp to the array ARR variable. So you will need a loop, and here you have to take care of the index being used for the temp versus index used for the back for the array, because the temp indexes are guaranteedly 0 to something and ARR indexes are start to end. Having said that, I think I can go back and now resume. So I'm sure merge sort implementation has been completed by all you. Those who could not complete and want to try based on the partial code which I have just shown, they should pause the video and try to do of their own. Those who have done or those who don't need partial code and those who want to see the complete code, let me show quickly the demonstration of the complete code. But those who want to try based on the partial code, give a pause, try that, and then come back to this video. So now I'm resuming with the complete demonstration also being shown for the merge sort. So just now I have shown the partial code. So here the condition, obviously when I'm going to recursively call, should be that L list has more than one element. If start is equal to end, that means one element. But if start is less than end, it means recursively I have to call. Once recursively called, the merging should take place, and merging here will be done into this particular form. So I equal to j, and this is all. Then the condition, obviously when both lists are non-empty, so I less than equal to mid and j less than equal to end. I'm going to copy element from array I into temp in one case. Other case, I'm going to copy the element from array j, second sublist, into temporary array, and j and k being incremented. Then copying the remaining elements of ith sublist, if at all remaining in that. This I'll copy. Similarly, the remaining elements of the second sublist to be copied. And then finally, now I have to copy back into ARR. So from temp, I have to copy back, but temp indexes must be 0 onwards. So I will be start to end because in ARR, the elements are at index start to end. But in temp, they are at 0 to k effectively, or 0 to k minus 1, where we have used k earlier. So equivalently, I can use that. And this should not be just kept as a temp I. That will be incorrect. I think this is good enough. Main I can easily make. Scanf, reading the elements, calling merge sort with start index as 0, end index as n minus 1, and then printing the sorted array. So having said that, let's go back and discussions to continue, and we will be going to the same next logic for this. So after discussing this, I am sure all of you are able to implement merge sort without much of a difficulty. Now let me go to the next sorting algorithm. And that next sorting algorithm is called as a quick sort algorithm. In fact, as the word suggests, it is quite quick, but don't think that this is the quickest algorithm. Yes, it is named quick because when the scientist Hoare, who designed this algorithm, he proposed this sorting algorithm to be quite quick, or one of the fast algorithm in different situations that was being considered. And I still say merge sort is again very fast, but it has a disadvantage that it needed one extra array. A big array needed. If n was big, we will need a big array, and that's a local variable needed every time in the recursion. So that's the disadvantage. Otherwise, merge sort is quite good. Quick sort, no extra array needed, and we will be able to perform it well in reasonable time. But of course, quicksort has its own disadvantages in some other situations, which you will study in detail when you do the detailed analysis of time complexity and all that discussions in design and algorithm you will study in more detail. So let's go to now quicksort. So Hoare designed the quicksort, and what we are going to study is there are different versions of quicksort. We are going to study Hoare's version. And the same version is given in Horowitz and Sahni book also. Of course, there can be some other versions. Why? We will just understand what quicksort means. So first of all, let's understand what is the definition or two-liner for the quicksort. I'll say first step it has is select a pivot element, and what we are supposed to do is we are supposed to place it at its right position somehow. What will right position mean? I'll explain. Right position means that all elements on the left of it they are going to be less than or equal to the pivot element, and all elements on the right of its they are going to be greater than or equal to pivot. So that becomes the right position. That will be step one. Step two. So effectively now, that effectively will mean I have a list. Say one of the element was chosen as a pivot. Let's say this element was chosen as a pivot. Say it was 15. It will mean I have to find suitable position for 15 somewhere in the middle, hopefully, such that this 15 goes here and it has got its left sublist. It has got its right sublist. And what is my requirement? I'll say now left sublist all elements are less than equal to 15. Right sublist all elements are greater than equal to sub 15. Hence, I can quick sort again the left sublist, and I can quick sort right sublist. You can easily see the word quick sort being reused while defining a quick sort. Hence, this automatically becomes a case of recursion being used. So I can easily see this will be recursion coming into picture. And in the recursion, of course, we always want the size to be reduced. I can easily see the sublist will be smaller than the original list. So definitely size is decreasing. And definitely stopping criteria has to be there, or when to recurse, repeating criteria. That cannot be unconditional. So we have to know the stopping criteria also. Obviously, in all sorting algorithms, if Only one element is in the list, no recursion needed. Nothing to be done, list is already sorted. Otherwise, we have to do that. So otherwise, we have effectively 3 steps. Step 1, which we have just explained above. Then I have step 2. And I have step 3, where step 2 and 3 are nothing big. They are just recursive calls. So I can easily see that step 2 and 3, without much of a difficulty, I will be able to do that. Let me just focus once again. Yeah. So I hope now it is visible clearly. And this is. So with this, I can easily see that this will work well. And let me just adjust the. So based on this discussions now, I can easily see that once we are ready with all these things, now I can try to explain and find how it works. So primarily, step 1 is what is doing the major adjustment, and that is what we have to understand. Step 2 and 3, things are simple. Recursive call will do that work for me. Step 1, let's assume some data and we will understand how does it work. I say there is going to be some data, say 15, then I have 3, then I have 19, then I have 4, then I have, let's say, 18. Similarly, I have some more data, let's assume 23, let's assume 12, then I have 23, then I have 7, then I have 9, and then I have, let's assume, 20. So I have this data. So this is my start index, and this is my end index. Initially, it will be 0, 1, 2, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 0 to 9, total n is 10, and I have 0 to 9 elements available at these indexes. So what Horace sort said, choose a pivot element. Horace quick sort. Pivot, which pivot? Pivot means what, first of all? Pivot means the element based on which we are going to probably make all the adjustment of the logic, and pivot element is a special element which is being discussed for the algorithm's functionality. So pivot word in general means you have a central point, you have a central stage, you have a key point. So that is what we mean by pivot element. So any one of them will be chosen, and that will be the central stage of the algorithm's working. In Horace quicksort, he said always the first element, the start element, will be taken as a pivot. So that's the change. Other variants of quicksort implementation can take some other place as a pivot, and accordingly, they are variations to the quicksort implementation. Similarly, how they will be placed into the correct position, that logic might be different with the different variants, and accordingly that can be done in this particular manner. So what Horace said, that now I will have one index I taken which will go left to right for keeping the left sublist, and J will go in the reverse direction. J will grow right to left. So I will be corresponding to list for lesser elements, or equal to also less than pivot elements list, and J will have the list, that is, this is left sublist, and this I mean as a right sublist. So I will maintain two sublists via I and J. It will be more clear once I take the same data again and start doing this. Let's see what and how it works. So this is my index 0, our start, 15, 3, 19, 4, 18, 12, 23, 7, 9, and 20. This is taken as a pivot. So I will have one extra variable taken, which I will say as a pivot. So that will be 15. I will be comparing with 15, and aim is to bring 15 at right position. Right position will obviously mean value 3, 4, 12, 7, 9 should be on the left of a 15, and values 19, 18, 23, 20 should be on the right of this. That is what right position for 15 will mean. So when I said bring it right position, for the time being, equal values I have not taken, but I will suggest, yes, for equality also you should understand. I'll explain in the discussion. 15 as an pivot. How do I bring it to right position? So what I'll say, let I start from here. I will start from next to pivot, and what my aim is, I will say if the value is less, it is already on the left side. So I will say I list will grow somewhere up to middle. Somewhere up to middle will mean all these are the smaller levels, and in between somewhere pivot comes, and J list is coming from this side. So J is on the right side, and J list will end somewhere up to middle. They will be having bigger values. So I say I will start I from this side. If the value is smaller, increment I because the value is correct. My aim is to find I to reach to a position that element is bigger than this, which needs a shifting. Maybe equal also. So equal also I will shift, but yes, equality we will talk a bit later. So I say, as long as the value is smaller, I'm going to keep it here with the ith list. And so I is here, I comes here, 3 is smaller than 15, go ahead. 19. 19 is bigger than 15, so 19 needs to be shifted somewhere towards right. So I will keep I and stop here, and I have found some element which is a misfit. I start now from J. J is 20. 20 is bigger, so this value is right side correct. Shift J. J comes here. 9. 9 is smaller than 15, so 9 is probably wrong side. 9 should be somewhere to the left side. So I will say I and J I have found, and both can be interchanged. So that will mean 9 comes here, 19 remains here. So now this is what is there. So my I was earlier here, J was earlier here, and now I will go further. I will say again, I will interchange. Now 9 and 19 interchange. Now I will increment I, go to next position. I is coming here. I is 4. 4 is okay. Shift I further. 18. I is having an element which is bigger than 15, hence it should go on the other side. 7. J comes here. J shifted. Now J comes here. So 7 should go right side, left side, and 18 so right side. So that means 7 and 18 have to change its position. So what I want is these two to be interchanged. That will effectively mean that I will have 7 here, 12, 23, and 18 here. So these two have interchanged their position, and earlier I was here. Now further I will go for the same process. Look for I to go to next position. I comes here, finds that at 12. 12 is lesser than 15. So 15 is already, 12 is already okay, no change. Go further I reaches here. Now, this is bigger. Probably this requires shifting. I'm using word probably because some stage will come, this exchange will stop. J was earlier to this place. Now J was earlier here. Now J will further shift and J will come here. J is still okay because 23 is bigger. J comes here. Now at this point of time, if J is once here, that I can easily see that now I have the two elements where probably I have crossed, I and J have crossed. Left sublist and right sublist have crossed each other. Crossed each other effectively means no further shifting will be needed, and effectively jth position is the correct position for pivot element. You can easily see now at this point of time, if this is the value, 12 is lesser than 15. So if a 12 comes in the place of 15 versus this, then I have everything ready. So what effectively what I need is, if I and J have crossed, after that, effectively my lists, sublists are almost ready. And once sublists are ready, then my pivot need can be placed at right position. To be placed at its right position. And right position effectively will mean that I need to swap array start versus ARRJ, because array J is the position which is showing a smaller value than pivot. Pivot comes here, smaller value goes in the left sublist. So this swap will bring the element at correct position. Remember, you are not supposed to swap in a wrong manner. What does that mean? I mean that you should not think of swapping it in a different way, meaning that sometimes you might think that let's swap pivot versus ARRJ. I say it will be incorrect. What you have to swap is array start versus ARRJ. Why? Let's see from the previous data. I'm putting the data here once again for your reference. This is what we were already targeting. So now I have a 15 here, 3, 9, 4, 7, 12 here, which is pointed by J, 23, 18, 19, and 20. I said, if you try to have a pivot interchanged, pivot is a separate variable where you have stored 15. So if you try to interchange 15 versus 12, it will be incorrect because a 12 will reach here, which will be not the correct position for the 12. It is an outside variable. What you are supposed to interchange is this versus ARR start. These two to be interchanged. This will mean 12 coming here. 3, 9, 4, 7 was already correct. 15 coming here. 23, 18, 19, and 20 were already correct. This will become my left sublist. This needs to be recursively solved. This becomes a right sublist. So obviously, I know my left sublist, this was a J position. So from start onwards up to J minus 1 will be my 1 sublist, and J plus 1 to end will become my right sublist. So having said that, now I can easily understand what logic and what programming I need to do. So now let's try to go towards the programming for the same. So now let's start doing the programming. So we are going to write the function void quicksort. Of course, you know now well what parameters I'll need with proper syntax, etc. So int, etc. Whatever you want to write, I'm not bothered about much syntax at present. Array is definitely needed. What else do you need? Now we are clear that we will need the starting index as well as the ending index. So both will be needed. Hence, simply passing n or 0 n will not be sufficient, or size will not be sufficient. We will be effectively passing or call initial call will come with 0 to n minus 1, but both indexes are needed because in subsequent calls to the recursion of quicksort, the start will change and it might not remain only 0. And end will also change for the left sublist, and start will change for the right sublist, and that change will be needed in every one. So first thing, what I need, do I need stop recursion to be implemented at all or not? Do I need the call to be recursively solved or not? Is there something to be done or not? If the list is not empty, only then I have to do. If the list has empty, nothing to be done. If list has a single element, nothing to be done. So first thing is, we will always program it by using the stopping criteria based check or condition on which the recursion will be started. Stopping criteria met means no recursion. So we will write reverse of stopping criteria to call the recursion. Of course, it has to be based on the size of the list. Size of the list is determined versus with start and end. So it has to be some condition based on start versus end. If the condition meets, I will be calling recursively and doing something, otherwise not. Now, start versus end. What should be the condition? Of course, if the list has certain elements, I am going to repeat. Maybe I can say something like this comes to my mind. Could be okay. I'll just put a question. Why do you need question equal to here? Equal to means start equal to and means a single element. Single element is already sorted, so need not do anything. So at any point, if my list has only one element, I need not do recursion, I need not find pivot, I need not place pivot. Hence, I can safely say this I can think of removing probably. I'll leave it to you to think more than that. If this is there, it means we are supposed to do solutions, do steps 1 and 2 and 3. Step 1 and step 2 and step 3, where step 1 was related to going for this corresponding recursive corresponding pivot to be placed, and S2 and S3 being the recursive calls to the left and right sublist. Step 2 and step 3 coding is much more easier. That will effectively mean just before this will be over, after this nothing to be done. So if the condition is true, I am going to have a quicksort recursively called. Recursively called means first sublist. First sublist will start with start and might end somewhere in between. Similarly, step 3 is simple. I have a quicksort recursive call where second sublist will have a initial index to be determined based on some variable ij, etc. And definitely list ends with the other side, that is end. So this step 2 and step 3 are easy. I can easily code that. Rest in between, I am supposed to write the code for step 1. Step 1 we needed what? Step 1 needed the pivot to be placed at its right position. Line 1 of the step 1 said find or choose a pivot. So what is our criteria? In Horace quicksort, my pivot is defined. What is my pivot? Pivot is ARR start. Now comes some important logic. What I am supposed to do? I have to use I for something. How I have to use I? What I have discussed is regularly I was shifting to next position. If the value were lesser, then I have said that it is on the right side. So I will say keep on incrementing I. That is the correct way of explaining this step until you find a misfit element. Misfit element in the left sublist is found. What does that mean? Effectively, this means that I am supposed to increment I and ensure that I always keeps on changing. If the value was okay, keep on increment I. If the element is a fit, increment I just. Fit element means what? If element is, or I'll say if array I is less than pivot, it is fit. It is okay. This can definitely remain into the left sublist. You could think of having equality also, but I'll not touch equality for the time being. And after a few minutes, we will talk of equality. So I say this is a fit element. That means if this condition is violated, I need not go further. I have found a correct I. Similarly, J also. Find or keep on incrementing J, decrementing J. And you have to find ultimately a misfit element, which ultimately effectively means that the corresponding element is misfit in the right sublist. To get J at misfit element, and misfit means in the right sublist, the element is misfit. And of course, then we said if they have not crossed each other, so something like if I less than J, again, equality could be thought of, we will talk later. If they have not crossed each other, if the left sublist and right sublist have not overlapped or crossed or reached to the same point, then of course I needed a swap of ARRI versus ARRJ. This process I needed to repeat as long as lists dot cross. So repeat, and I must always keep on doing this. So ideally, I will say here it should be a do while loop. Why do while? That first time I should reach and definitely go further. Regular progress should be always guaranteed. So you could think of having a while also, but probably do while is a more clear picture to tell why, because I have to ensure every time when I come out of the loop, that time my J is at least at its correct position where I can swap the pivot element's position, which was array start. And we have already said that we have to swap this value with array J. So what I give you a hint is that while loop will be much more useful to ensure that in all positions, J reaches to the correct place. Why I am saying? For sorted data also, or for reverse sorted also, and for any other also, we must ensure that J must be at correct index. And correct index means the correct position of pivot element. So this is one special logic where do while becomes much more meaningful and useful, where we can see. It will be more clear when I focus on one step each. This step, how will I find and change I? Again, you could think of using a while condition here. Some of you might have tried with while also. Those who have, or maybe I'll say, first of all, now based on this, try to write logic and test for all different type of inputs. I have already discussed in selection sort, insertion sort, etc. 8 to 9 different test cases, different types of inputs. Test that, try that, and you might find some problem. Especially, I will say, always you must try for data like all sorted data. Let's say 1, 2, 3, 4, 5, 6, 7, 8. Does it work well or not? Reverse sorted also. Say 8, 7, 6, 5, 4, 3, 2, 1. Does it work well or not?
Then I'll give you some special data like say 1, 1, 5, 6, 7, 8, 1. Maybe in some special cases, your data or your program might fail. Then you will understand that you are making some mistake, because this is one logic where equality of the data can create a problem. And we will talk of that after a few minutes. But before that, let's focus on the step which how to code this. So those who want to try, they should pause here and try to write the full code of your own. After that, you can come back and see what step or what logic I write for these in between steps. So I'll say I step, how to increment. So those who have paused, I'm giving you time, do this. And now once you resume, I'm explaining what we will do. Increment I, keep on incrementing I. I say this can be a simplest way to use do while. And this is one situation where if you try using while, you might make some mistake because it might remain into the loop in some special data. But you have to ensure every time I resumes from next element wherever you earlier stopped. So I'll say do while. Do while what? Maybe I want to say if element is less than pivot, this is acceptable in the left sublist. So this should continue and increment. There is a single statement, so I need not put braces. Even if I put braces, that will be fine. You have to put a semicolon. You should remember this. But I say this condition is incomplete because in this process, you might happen to cross the list. For example, if you are talking that you have array I always less than pivot. For example, 8 is a pivot and your I comes to 7. Array I is less than pivot. I will increment further. Less than pivot, increment further. You will reach to this point and then you will reach to next I, which is out of your array. So you have to ensure that you never go out of array. For that, I must have a condition, say I less than equal to and probably and this condition. So approximately this condition, you have to check whether this condition is okay or not, but maybe this is one of the way to do that. So this way I am doing this. Now you could think of doing this using while loop also, but for equality, equal data, it might create certain issues with that I'll explain after a few minutes. Similarly for the other step, this also I can say it will be also similar. Do j minus minus. Do j minus minus while what? While I have the reverse condition, array j greater than pivot. If the element is greater, that means element is already on the right side and perfectly okay, so need not bother. As soon as I get an equal value, the quick sort suggests even equal values can be interchanged. For the time being, they are all unequal values like this, or I have some data 5, 7, 9, 3, 2, 11, 4, like this. All unique values. So I can easily see misfit value like I'm typing of 5. 4 is a misfit on the right side. So 4 must be shifted. 3 was a misfit on the left side. So 3 and 4, 7 was a misfit because the 7 is not smaller. So 7 is on the wrong side. So 7 and 4 will require an interchange. So this will be repeating. And now once I have done this, then based on that, rest of the logic will happen. That should also tell what should be the initial value of I. Initial value of I must start with start. Reason being, first time I'm taking I at a start, immediately I will be guaranteedly incremented. So my comparison will start with next to pivot always. J must always start with the last element to be compared at this condition. Hence, my J must be initialized 2 and plus 1 because J will be decremented first. So array J greater than pivot. Some of you might be wondering, should I have a condition here j greater than equal to start also or not? I say yes, you could think of writing this, but not needed in this coding. For j, it will not be needed. Why? That is where this equality matters. I say I am writing to find an element if it is greater than j is decremented. Once you reach to the pivot position, say you are coming for the data 5, 7, 9, 3, 2, and so, say you are coming for, let's say all this data was bigger than 5. You are coming like this. J is a decrementing. 5 is the pivot. Array j greater than pivot. Yes, decrement j. Array j greater than pivot, decrement. Array j greater, array j greater. Once you reach here, j has come here. J will be decremented. Now j has come here. This condition is guaranteedly going to be false. Because once we reach to j at pivot position, start position, array j is 5 and 5 is never guaranteed, 5 is guaranteedly not greater than 5 itself. So at this point, loop will guaranteedly terminate. So what I have to ensure is always that I or j's loop is not infinite. One thing, that must not be infinite loop. Secondly, in all cases, I and j keep on progressing. They should not stuck at particular point. With equality value, the stucking issue can come. Hence, we have not included equality here, or in this case, equality helped me in reducing one condition also. But whatever logic you implement, even if you don't write a do while, you have to ensure that this is also guaranteed. Having said that, I will say now it's right time to pause again and you should try to do coding. So I'm giving 2 seconds pause. Those who want to do, they should pause the video and try to do the coding and complete this coding. Those, once you come back, I will show the partial code for this particular case. So again, I say those who want to try, they should pause the video and try that. Now I'm assuming that you have tried and you need some help or you want to verify whether you have done correct coding or not. So I will show you a partial code, and of course, full code I will show in the next lecture. So this is a partial code for my quick sort. My function, if I need a prototype, because I'm calling the function before it's declared, so I have made a prototype. Array red, all elements red. Array quick sort called with 0 to n-1, starting index being 0, ending index being n-1, and then display. Of course, I need not make it int. I can be simply main, return 0, etc. need not be there. I can safely do without that also. Although main is also a function, so it can also return. Function, quick sort, start and end past, condition. We have already discussed that equality could be one choice, but equality whether needed or not, you should decide. Pivot found, I to have starting value, j to have starting value, and then I say I need a do while loop. While I less than j. Of course, you could think of having equality also. Will that needed or not? Is that useful or not? You can think. But I need I to shift every time, ensuring that once after one change happened, next time again I shifts. I doesn't get stuck to some position. Hence, do while ensures I is guaranteedly incremented before any condition is checked. Similarly, do j minus minus. If they have not crossed each other, then I can swap the values. Ultimately, array start to be interchanged. Most likely, we could say that this is going to be array j. And if so, then I have to ensure that j is always at correct position. I should not put any special condition here. That will not be a good logic. This has to be always done because pivot is there. So in worst case, if pivot is at right position, j must point to the
pivot index, that is start itself. In that case, swap with itself will happen, no problem. So I can always do that. And then my recursive call. Recursive call now with the left sublist and right sublist for the second recursive call. Left sublist. What is the left sublist? I can easily see that my left sublist is always now just before pivot. That will effectively mean j minus 1. And my right sublist is after pivot. That will mean effectively j plus 1. So you could see slowly my list is reducing and doing like this. So having said that, now I think it's the right time to discuss some final touch related to programming that comes in terms of equality related issues also. So now I'll stop here and go back to the discussions. So now let's talk of the equal values or duplicate values also. That is also one special situation where you have to be careful, otherwise your programming is likely to become wrong for certain special data. And this concept is also related to the stability also of the quicksort. So we will talk of sorry. We'll talk of both aspects. For example, I say I have value 5, 6, 7, 8, 9, and let's say I have here also 5 and here also 5. Now, this is a pivot. Of course, final output will guaranteedly require these all 5s to come in this form like this. But now what my quicksort says, first time you start your I here. What logic we discussed was this element will be skipped only if it was less. Only if it was less means with value 5, I will stop here. Do while will stop here and I will stay here. Similarly, when I come from this side, j is outside. First j minus minus will happen and j will reach to this. And I said if array j is greater than pivot, only do while loop will execute again. But because this is equal to pivot, as per my just discussed logic, it will stop here. Why I am stopping here? That now these two will interchange as per what we discussed. So this will become 5. This will become this 5, but interchange has happened. But next time I should not remain I and j on these places only. And if you use now, you can think if had you used while condition for I or while condition for j, probably you might have made a mistake and you could be into infinite loop where I will not progress if you write while I array I less than pivot, or if you write while array j greater than pivot, they will not shift further and my progress will not happen. Yes, you could think of introducing some equality there, but that will probably create some more problems. But yes, solution is possible through that also. But this is guaranteedly to work correctly. And that is the best practice of programming, that now using a do while and using not equality in the condition, still it is guaranteed that my I progresses and j progresses. And while explaining, I always said that after exchange, next time, next elements will be compared. In my explanation of the quicksort, that was the logic. So based on the logic, my programming has to ensure that I and j progress again. In this case, they will ultimately keep on going, and then finally we will have all that work done. So just because of that, we will take care of that. So taking another data, let's say I have 20, I have 40, I have say 10, I have again 20, I have 16, I have 25, I have 20 again, I have 40. This is a pivot. So for equality, let's bother what will happen. I will come here, 40 is greater, and greater or equal to, I am going to stop I. Less than, I am going to ignore and increment I.
This side 40 is greater, ignored. Equality, I stopped. This 20 will be stopped. For equality, I am trying to keep J here, I is here, and both will stop and they will interchange. This will become 20, this will become 40, and now I will be guaranteedly shifted to next position. J will be guaranteedly shifted to next position. This value is lesser, so J will further shift. This value is not lesser, I stops here. 25 is greater, so J will shift. 25 is ignored, it is right side. 16 is lesser, J will stop here. So now my I is 20 and J is 16. They have not crossed each other. Again, this will become 16. This will become 20. So now my new data at present, this is pivot, this is this, 25, 20. Sorry, this has become 40 and this is also 40. So this is 40, this 40, this was 25 and this was already there. So this changed to 20, this as it is. Now my I is earlier this was a 20, this is 16. They have interchanged their values. Earlier these two interchanged. After interchange, now I will further progress guaranteedly. So I will stop at this point because this value is not lesser. J will also further progress guaranteedly. J will stop at a value lesser. J is here. So this is J. And now I can easily see that a pivot versus array J interchange will happen. 16 will come here. 20, 10. This comes a pivot. And other side is values this. So this is my left sublist. This is my right sublist. And you can easily see equal values are present in the less than or less than or equal values than pivot are in the left sublist. Greater than or equal values in the right sublist. So my definition of quicksort said that left sublist can have less than or equal to, right sublist can have equal, less than or equal to. Now just you see, is it a stable sort or not? And if you remember, stability meant that relative ordering of the records with the same key comparison value, are they preserved in that order or not? So this is 120, this is another 20, this is a third 20. I will say my quicksort will be called stable if these three values finally remain guaranteedly in this order. So guaranteedly this order will mean that wherever they reach finally, it must be ensured that only this 20 was first, then this 20, then this 20. Is it happening or not? Will it be guaranteed or not? I leave it to you to think over this and accordingly read also from the book. If you try to explore and if you find it is unstable, then try to think what changes would you think. Will that really, somewhere you bring equality, somewhere you remove equality? Will that really solve the problem of stability or not? You have to read in more detail. And then you will be able to appreciate what is the issue related to this. So that much your self-reading will be desirable. I stop here. Try to do whole complete coding. And if you need any assistance, next class I will show the final code for the quicksort. Bye-bye. All the best. All the best to all of you. And let me stop recording.